Okay, we will get started. Wrapped up DC circuits last week, actually Monday of this week. And we talked about resistors and capacitors in the circuits. There's another fundamental passive element in circuits that we're going to consider called an inductor. An inductor is used in a similar way that a capacitor is used to add a time dependence to a circuit. But we can't study inductors until we understand the fundamental principles that they operate on, which is magnetism. We haven't covered magnetism yet. So the title of this course is Electricity and Magnetism. And you'll often hear electricity and magnetism together when you're talking about physics courses or books, or the study of electricity often accompanies the study of magnetism. We'll learn why today. So we're going to introduce magnetic fields, just like we introduced electric fields to start the course. And then we'll talk about dynamic effects and how inductors use magnetic fields to store energy. Okay, so a new concept means new terminology. Magnetism and magnetic field. Just like the electric field had field lines and flux associated with it, so will the magnetic field. We'll study the motion of charged particles in a magnetic field, and that's probably as far as we'll get today. And then next Monday, we'll talk about the Hall effect and other effects related to magnetic forces on moving charges, including current-carrying conductors, so wires, and the torques that the magnetic force can exert on a current loop. And it's very important because that's what gives rise to electric motors. Okay, so some of the things that we'll introduce today are magnets, both permanent magnets and electromagnets. We say that magnets are dipoles. So we talked about dipoles with electric dipoles. So we'll refine a little bit what that means and contrast it with monopoles. There are no magnetic monopoles. The units of magnetism are Tesla and Gauss. The units of flux are the Weber. And by the end of this chapter, you guys will be very familiar with the term solenoid. So that's something you can tell mom about. Okay, so magnetism. What is magnetism? Magnets are these things we played with as little kids and ever since, and they're kind of magical. But what do we know about magnets? What makes a magnet? I mean, if I give you a little chunk of metal, how can you tell me whether that's a magnet or not?
It attracts metals.
It attracts metals. Okay, Antonio?
Yeah.
Same thing? Okay, so you stick it to metal. Does it attract all metals? No. Themselves towards the north and south poles of the Earth's magnetic field, and that's why they can rotate to a line. But one of the most fundamental properties of magnets that's sort of covered in this, but not explicitly, is that they're dipoles. So what does that mean? We know that magnets can have two ends, a north pole and a south pole. So if you take two magnets and you try to stick them together, they'll either stick together or they'll repel, right, depending on how they're oriented. And so we like to say that there's two polarities, a north and south, and north will attract south and south will attract north, but they'll repel each other. So two south poles will repel. But the same thing could be said for electric charges, right? There's two types of electric charges, a positive and a negative, and they'll attract each other, but like charges will repel. Okay, so the difference is magnets always have these two poles in the same object, right? Whereas an electron and a proton you can separate. What happens if you try to take this magnet and split it in half? What happens if you try to cut off the north pole and separate it from the south pole? Yeah, you don't get that. You get two magnets. When you cut it here, you still have this north pole end, and this just becomes the south pole. And since this was the south pole over here, you end up with a north pole right there. So you cut these things up, and you don't get separate magnetic charges. You get separate magnets. Hugo?
At this point, a student is asking a question saying, I once broke a magnet, and it stopped being magnetic.
How did you break it? Okay, so one of the interesting properties of magnets is that the magnetization can change when you induce shock. So if you hit it with a hammer or something, you may have actually just changed the magnetic structure of one of them. Okay, so magnets are always observed to have both a north and a south pole. There's no fundamental reason that we know of in nature that tells us why this should be. It's just an empirical observation. A lot of people spend a lot of time searching for isolated magnetic monopoles. A monopole would be just a north pole or just a south pole in isolation from its partner. No one's found any. So that's different than charges. If you have a hydrogen atom, which is also a dipole, it has a positive and a negative, you can split that apart, right? And then you can have those separate monopoles. You can have a positive and a negative, but not with magnets. So we'll see a little later that that observation has a profound consequence on some of the laws that we're going to derive and use to describe magnetism. Okay, but first, let's explore a little bit more the relationship between electricity and magnetism. So here I've got a compass and a wire and a DC power supply right here. So this DC power supply is essentially plays the role of a battery. Now that compass has its needle pointing north. Let's see. There we go, that's north. So out towards San Fernando Street is north. And I put this wire over it. Okay, now that wire is not connected to the magnet. It's just sitting on top of it. The needle moved, right? The needle responds to magnetic forces. So there is some connection between the electricity flowing and the magnetic field. Okay, so now we see another example of a connection between electricity and magnetism. Basically what we showed is that electricity can produce magnetism, a magnetic field in this case. Okay, and that was the discovery of Oersted and Ampere. So Ampere we know is the unit of current flow, and Oersted is actually a unit of magnetic flux. So these guys had a fairly profound discovery that led to their names being attached to various units. Okay, so electricity can cause magnetism, which is interesting, but there's more than that. Let me set up another demo. Over here, I've got an ammeter. Big ammeter, so you can see this. And I've got the leads for this ammeter going to this coil. And then I have a magnet. Actually, it's a very strong magnet. So I'm going to try not to drop it near any metal, 'cause it'll be hard to get off. Let's watch what happens when I move this near the coil. It reads current through the wire. Let me do that again. Let me turn it over. Okay, I was dropping it that way. Let me turn it over and drop it this way. You notice the difference? So the magnet produced electricity. So we have an electricity producing magnetism. We have magnets producing electricity. So you can see this connection. Okay, so a moving magnet going through a coil of wires produces current through that wire. And in fact, we can combine these two effects, which is kind of fun to do, so I will do that. I'm going to take my DC power supply, and I'm going to connect it to this coil of wires. So this is no different than that coil, it's just thinner. So having a coil of wires is a little bit like when I had this wire sitting over the compass. The wire, when it had current flowing in it, produced a magnetic field. Having this coil is essentially like having a lot of wires in very close proximity. Okay, so now what I'm going to try to do is I'm going to try to use my electricity to produce a magnet, use that magnet to produce electricity. Okay, and we'll see it there. Now, it turns out that this current only goes up to, or this voltage only goes up to 12 volts, which isn't quite enough to get dramatic readings. So even if you see a very small effect, please applaud. Turn up the current a little bit. All right. Okay. So we'll look at that geometry in quite a bit more detail in coming chapters and do lots of problems involving it. But really what I want you to take from this is electricity can cause magnetism, magnetism can cause electricity, so these things are intertwined. Exactly how was really not understood until the mid-1800s. And this class covers essentially everything up until that point. So if I time everything right, then on the last day of class we'll have a review, but the day before that we'll combine everything we've learned and present Maxwell's equations. So George Clerk Maxwell was the Einstein of the 19th century. He took all these little pieces of understanding that were isolated in themselves and combined them into his uniforming laws. They really describe all of electricity and magnetism. So that will be the climax of our class. But until then, I just want you to make that connection. Electricity and magnetism are linked. So you can have things like electromagnets. You can have magnets made of current. And so oftentimes you see exactly this configuration of a coil, where that coil looping around essentially increases the number of wires that are contributing to the magnet. And oftentimes that magnetic flux, the field lines that are generated, are guided through an iron core. And you might have another coil over here, and you can use these things for like picking up a car, for example, or dropping it when you turn off the current. It's a magnet you can turn on and off. But before we talk about electromagnets, let's talk a little bit about permanent magnets, since those are the ones we're typically most familiar with. If electromagnets are caused by current flowing in wires, permanent magnets should be caused by something similar. And in fact, they are. They're caused by moving charges. Okay, current flowing in a wire is a moving charge. And in a permanent magnet, it moves in the sense that it spins. And spin is maybe not the best word. There really is no good word for what's going on. There's a quantum mechanical property called spin, and we can associate that, or we can make the analogy that that's like a spinning charge. So a moving charge, or a spinning charge in this case, is what's causing the magnetism. And we can think of a spinning charge as like an electron moving in a circular path. It's a similar idea. An electron moving in a circular path is much like the current flowing in this coil of wires. So essentially, this is like a little electromagnet, but we're not driving it with some battery or power supply. It's sort of powered by the quantum mechanical spin of the electrons in it. Now, in most metals or materials, the electrons that are in the material have a tendency to align or anti-align with each other. One acts like a little magnet with its north pole pointing up, so the next electron will act like a magnet with its north pole pointing down. That's the most energetically favorable configuration, and those two things cancel each other out. And so when you have a whole bunch of these, you have no net magnetism. But in certain elements, particularly those in the middle of the periodic table, over here, when you start adding up the electrons in their outer shell, and this is something that you may have done in chemistry, it's not something we'll go into any detail in here, although if you take Physics 53, you'll cover this in great detail. In the middle of the shell, what happens is, as electrons get added to the outermost shell, they have to have different quantum mechanical states. And the first thing they do is they all line up with the same spin. And then once the shell is filled up halfway, the other half is filled up with the anti-aligned spins. And so you get very few unpaired electrons over here and over here, but in the middle, you get the maximum number of unpaired electrons. Hugo? Yep. Nickel, cobalt are common ones. platinum, iridium. Those are common. Those are the common materials used in permanent magnets. Iron. Okay. So a little bit about how magnetic fields get created. A moving charge creates them, whether it be a current in a wire or a spinning charge in a permanent magnet. That's what creates the magnetic field. You need a charge, and it needs to be moving. Okay? We already saw that a moving magnet produces a current. Now, a moving charge produces a magnetic field. So those things, there's a symmetry there. A moving charge produces a magnetic field in the surrounding space. That magnetic field exerts a force on any other charge that's present. Okay, so if I have a magnetic field from a permanent magnet, and I slide it through that coil, the magnetic field is going to exert a force on the electrons in this wire. That force is going to move the electrons. Those electrons flow. That's a current. Okay, so magnetic fields exert forces on moving charges. Now, you might say, well, the charges in there, the electrons aren't moving. There's no current flowing, right? And so if I set this there, I've got a magnetic field, and I've got charges, but the charges aren't moving. So there's no current flowing. When I move the magnet, the charges still aren't moving. So how come I can get a current flowing? Let me phrase it this way. The charges aren't moving relative to the table, but they are moving relative to what? The magnet, right? So the charges can be moving or the magnet can be moving. That's sort of a symmetric situation. And we can represent magnetic fields by field lines, just like we do with electric field lines. But electric field lines started at positive charges and then always ended at negative charges. Well, magnetic field lines are similar. They start at the North Pole and end at the South Pole. But every magnet has a North and South Pole. So what that means is every field line comes in and closes on itself. So magnetic field lines always loop around. They never start or end. Okay, so look at those three statements. Digest those three statements. And help me figure out an expression for the magnitude of the force that can be exerted on the magnetic force of a moving charge. Okay, so on a moving charge. What thing should that depend on? Okay, B. What is B? B is the magnetic field. Okay, so that's going to depend on how strong our magnet is. The magnet that's producing the field that the charge is moving through. So it's going to depend on that. What else is it going to depend on? Q. So it's a function of these quantities. I don't know what function yet. What else? What is A? The area of the magnet. Okay, we'll put that in. Well, I've got a moving charge. I didn't say anything about the path that it's moving in. And in fact, we want to find the force for just a freely moving charge. So it may not even be in a wire. It might just be an electron flying through space. Well, that would give us an electric force. There's one more thing. The velocity. We want the force on a moving charge. So what's actually going to be important here is how much it's moving, v. Right? If v equals 0, we expect the force to be 0. So let's see if we can come up with an expression for this. Should that force, how should it depend on the charge? Directly, okay? Greater the charge, the greater the effect. The charge is 0, there should be no force. How about the velocity? directly, same deal. If it's moving, there should be a force. The faster it moves, we might expect the greater the force. And how about the magnetic field? Yeah, okay, so all these things should be proportional, just based on the understanding that we put together so far. And in fact, they are. Okay, so the force is proportional to, and we don't know what that constant of proportionality is. It's going to have to be something that works out to give units of force. But it's proportional to these three things. But there's also something about the direction, right? This is just a magnitude. But force is a vector. It has a direction. And the direction of magnetic fields is really a little peculiar, the direction of magnetic forces. So empirically, what's found is that the magnetic force is found to be in a direction that's not in the direction of the magnetic field, but perpendicular to it. And not in the direction in which the particle is moving, but perpendicular to that as well. So how can we come up with a vector that's perpendicular to the direction of the field and perpendicular to the direction of the motion? Cross product. So, let me see. If vector C is vector A cross B, that means C is perpendicular to A and B, and has a magnitude of AB sine theta. What do you get if you cross a rabbit with an elephant? Rabbit, elephant, sine theta. Okay, so the force is proportional to QVB. V and B are vectors. Q is a scalar. And so let's try taking V cross B. That's a quantity that's proportional to the magnitude of it's proportional to the speed and the strength of the magnetic field, and has a direction that's orthogonal to both of those. So it satisfies this requirement that the magnetic force be perpendicular to those things. And so as a reminder, how to find the direction of a cross product, we're going to use the right-hand rule. So the right-hand rule says if you have A cross B, you take the fingers on your right hand and you point them in the direction of the first vector, A. Okay, and then you want to orient your hand so that when you bend your fingers in, you can move them so that they're pointed along B. Right? So for me, I have to orient my hand like this. And your thumb, when you stick it out, will point in the direction of that cross product, which in this case is into the page. Okay, so someone always gets points off on a test because they accidentally use their left hand. Their pencil was in the right hand. It's the right-hand rule. It's called that for a reason. Make sure you're always using your right hand. You always start with the first vector, cross into the next. We're going to use the right-hand rule a lot from this point forward, both for cross products mathematically and just for finding the direction of fields and forces and charges, and not charges, they don't have direction, fields and forces, and the direction that charges will move when we're just trying to figure out directions, not really do mathematical solutions. So it's important that you be able to do this. And it's important that we be able to represent these three-dimensional directions. I mean, we've got A and B in the plane of the paper. That's no problem to draw, but the cross product points in. So we need a way to represent that without having to wear 3D goggles. So we use a little circle with an X through it to represent into the page, and a circle with a dot to represent out of the page. And that notation comes from the idea that if you had an arrow with a tip on one end and feathers on the other, and you shot it into the page, what you'd see is the cross of the feathers sticking out. Whereas if it were shot out of the page, you'd see the tip. Okay, so I'll use that notation to represent into and out of the page. Okay, so magnetism has units. I mean, if we can calculate it, we can calculate the force It comes from a magnetic field. That magnetic field has to have some units on it. The SI units, the MKS units, are the Tesla. We abbreviate that capital T. Tesla is a Newton per amp meter. So, we can get a sense of what the constant, what units the constant is going to have at this point. Let's see if we can figure that out. If charge is in coulombs, velocity is in meters per second, and magnetic field is in Tesla, which is a Newton per amp meter, we need the force to be in newtons in MKS units. So we're going to equate these two expressions and compare their units. And we can rearrange this a little bit. This per second, we can combine with the coulomb. And now, what is a coulomb per second? That's an amp. And we have amps over amps, meters over meters, and newtons. Okay, so that sort of validates our assertion that the magnetic force is QV times V. So although the standard units, the MKS units, are Tesla, you rarely see magnet strength quoted in Tesla. It's more common to see Gauss. So a Gauss is 1/10,000th of a Tesla. Now Gauss is much smaller, and that's why it's more frequently used. It turns out the Earth's magnetic field is about half a Gauss. So here it is in a table. And that's sort of representative of typical magnetic strengths, magnetic field strengths that we'd likely deal with in problems or in papers. So if it's about half a Gauss, it's much more convenient to write half a Gauss than it is to write, 5 times 10 to the minus 4 Tesla. Okay, so if we look at different types of magnets, we have things like the Earth's magnetic field. That's a fairly small magnet. A bar magnet, like you might get at a hardware store or something, might be 200 times stronger than the Earth's magnetic field. A big electromagnet, the kind of thing that could lift up a car, has a field that's on the order of Teslas, so 10,000 times stronger than the Earth's magnetic field. If you go into an MRI machine, you might get up to 10 Tesla or something. And that's about it. That's about the strongest magnetic field that a human would encounter. Beyond that, these are things that occur inside stars, places you're never going to go. So for the most part, a Gauss or 10 to the minus 4 Tesla is a characteristic strength of a magnetic field. Okay, so let's do an example. Let's calculate the magnetic force on an electron. That's a moving charge. That's a charge. And we'll say it's moving at 300 meters per second. Turns out that's about how fast an electron moves when it's at room temperature. And it's moving at 30 degrees relative to the direction of a magnetic field. The magnetic field is the magnitude of 1 Gauss. So that's not unlike the magnetic field of the Earth. And this is an electron essentially at room temperature, so this is a very typical scale for these quantities. Okay, so we're going to use force as QV cross B. The charge in this case is an electron. Right? So the charge of an electron, remember, is minus E. We plug in minus E. The velocity we're given, 300 meters per second, so we can plug that in. And the magnetic field we're also given. And if we want to find the magnitude, we can use the magnitude of a cross product is quantity 1 times quantity 2 times the sine of the angle between them. So we have the magnitude of V, the magnitude of B times the sine of the angle between them. OK, so plug in our numbers. E is 1.61 times 10 to the minus 19 coulombs. Velocity, 300 meters per second. Magnetic field of 1 Gauss, which I need to convert into Tesla. Right, if I want my answer to come out in newtons, and I'm using MKS units everywhere else, I need to convert that into newtons. Yes?
Did you say 1 Tesla is equal to 1 Gauss times 10 to the negative 4? Or
1 Tesla is equal to 10 to the 4 Gauss.
10 to the 4 Gauss?
Yeah, a Tesla is much bigger than a Gauss. So 10,000 times bigger. So I have 10,000 Gauss equals 1 Tesla. So this quantity is magnitude of 1. And sine of 30 degrees is 1/2. Okay, so multiply these things together, and I can get the magnitude of the force. All right, so that magnitude is 2.42 times 10 to the minus 21 newtons. Sounds like a small force. It is, compared to the types of forces we're used to dealing with. But then again, this electron has a very low mass compared to the things we're used to dealing with. So even a very small force can cause it to accelerate tremendously. So we also have to note that this is a negative value because I had a negative charge. So this is just the magnitude. I have to find the direction now. And from that, for that, I do the cross product V cross B. So right hand, fingers pointing along V, curl them into B. Your thumb points in the direction of the force. So can I say that this electron is being pushed out of the page? The right-hand rule certainly says so. V cross B is out of the page. So how come the answer is into the page? Yeah, the magnitude I calculated over here was negative. It was negative because I had a negative charge. And as a result, the direction I get is just the direction of this cross product. But this Q in the front is where the minus sign came from. So minus into the page, or minus out of the page means into the page. So when you quote an answer for a problem like this, it's important that you be clear on what you mean. So I can say 2.42 times 10 to the minus 21 newtons into the page. I think that's the most clear way to say the direction of that force. I could say it's minus 2.42 times 10 to the minus 21 newtons, but that doesn't tell me what direction is positive. So it's usually easiest just to give it as a positive number and then literally say the direction. What direction would the electron be pushed if my magnetic field were into the page? So use your right hand rule. Let's see. V cross B points this way, minus to the right. Okay? How about if B were pointing to the left? So let me see all your right hands in the air. Okay. This is like the physics version of like a rock concert. Okay, so if B were to the left, V cross B would be out of the page. The force then would be into the page. Okay, good. Okay, so the magnetic field here was pointing up. We were given that, but is there a way we can determine that if we're given the magnet rather than the field it produces? So we can use the rules that we have for field lines. So there's two rules we have now. The rules are the field lines come out of the North Pole and go into the South Pole. and they always form closed loops. So if you have a magnet that looks like this, you can draw the field lines like so. Right, that's one. Goes all the way through. I can draw as many as I want. They're all going to have the same basic behavior. They come out the North Pole, circle around, and go into the South Pole. And you can see from this picture where the magnetic field is the strongest. It's strongest where the lines are closest together. So you get the most flux through a surface near the poles. And when you either get far away or you get closer to the middle, you're going to have a greater spacing of the field lines. So, yeah.
How come when you put like a magnet on like another side, it wouldn't like roll all the way around to the south side?
Let me see. So I put another magnet, like say down here.
No, like let's say you put one like right there. Would
Okay.
it like go all the way around?
Okay, well, first of all, if I put another magnet there, it's going to tend to align itself to the first magnet.
Just like a charge like
Just a charge?
charge or like something. Never mind, I don't even know.
Okay. Well, let me answer this. Let me make my own question. If I put another magnet there, it's going to flip so that it's oriented like this. The South Pole is going to attract to the North Pole of that. And so it'll find its way into that orientation unless I'm really rigidly trying to hold it in some other orientation. And when it's in this orientation, what's going to change is the field lines now get guided through the entire thing. So it doesn't look all that different. It's just like I've made the magnet longer. Yeah?
When you force two magnets, like say the two north ends together, and they don't want to do that,
Yeah.
what are they giving off?
A force. There's a force, a repulsive force between them. And that comes from, the easiest way to understand that is they try to minimize the energy. So we'll talk a little later about the energy stored in the magnetic field. But essentially, we can understand it qualitatively. If we try to force the north pole of two magnets together, and we have this rule that the field lines have to leave the North Pole, then they're kind of forced to do something like this. And what I end up with is a very dense region of field lines over here. And in that high density region, there's a lot of energy stored. So there's less energy stored if this flips around. Okay. Okay, so permanent magnets, though, aren't the only thing that can produce fields. Wires carrying current can produce fields. So let's see. Here's a wire with current going through it in this direction, and here are the field lines it produces. So this might look a little odd. Those field lines don't come out of a North Pole or go into a South Pole like they do over here in the bar magnet, but they do loop around. And so you wouldn't really talk about this wire having a North Pole or a South Pole, but it can still produce a magnetic field. It just circulates around the wire. Okay, so now imagine you take this wire, and actually before we imagine anything, let me point out that the direction of these field lines can be found from another version of the right-hand rule. Just take your right hand, this time point your thumb in the direction of the current. And when you do, if you curl your fingers will be curling in the direction that the field goes. So in this case, if the current's going into the page, the field will be clockwise. Okay, so if you can, imagine this wire now wrapped around itself to form a coil. And at any point, we can look at the current in the wire and the direction that the field would go if it were just a single wire. All right, so consider this wire right here with current flowing up. Would the magnetic field, in this region, would the magnetic field be coming out of the page or into the page? Out of the page. And how about over here in the middle of this, this loop right here? Would it be going, what way would it be going? Try to imagine this 3 dimensions. So the faces of the loop are like this. This is in the back. This is in the middle. What direction is the field going?
Right.
It's going to the right. Okay? And that's actually what we've drawn here, is the field going to the right. And now you take the next wire over, and it also has the current going up. It also produces a field going to the right. In fact, all the wires in the back produce fields going to the right along the axis of that coil. And the fields in the front have the current flowing down. So the same analysis says point your thumb down, and behind the wire, the current must be, or the field must be going to the right. So the field from all these wires is all adding up, pointing to the right inside the coil. And the same is true for the current flowing through the top and bottom. You can check that if you want. At the top, current is flowing out of the page, so the field is going to the right. So all these wires are producing fields that inside the coil add up to the right, and hence I get a flow of field lines going through the coil from left to right. And then when they leave the coil on the right, they must loop around. And so this looks a lot like that. In fact, it looks identical to that. So now you know why this coil of wire acts like a magnet. When you wrap up the wire in that particular geometry of a coil, you get field lines that circulate around, just like if this were a bar magnet. So this is called a solenoid, a coil of wire that's used as a magnet, an electromagnet. There are some tricks you can play with the magnetic field. Magnetic field tends to be guided by ferrous metals, by metals that have a lot of iron in them. And so if you take an iron rod or an iron, whatever shape that is, that's a loop of sorts, and you put the coil around that, when you put current through the coil, you've produced a magnetic field that goes through the axis of that coil, like we just showed. But now instead of just looping back around, it's guided by this iron core, and you can actually sort of channel the field wherever you need it to go. And so you could deliver it here through that little gap. And that's actually what's done. This could be like a read-write head of a disk drive or something like that. So we have a chance to see another use of the right-hand rule for a coil of wires. So the coil of wires over here, we could figure out which direction the field would go by considering the right-hand rule for a straight wire. And at any point in this coil, that will tell us which direction the field is going inside the core. And from that, we can figure out how the field looks. But there's a more direct way. Once you know that a coil of wires, a solenoid, has this magnetic field pattern that looks like a bar magnet, then you can use another form of the right-hand rule. Curl your fingers in the direction that the current in the coil flows. In this case, with my right hand, that is like so. And that leaves my thumb pointing in the direction that the field goes inside the core. That's true whether you have a solenoid with lots of coils or whether you just have a single loop. So a single loop is exactly like this, just shorter. Right? So take this straight wire that has a magnetic field circulating around it, and now bend it in a circle. And at any point, you see the field circulate around it. And on the inside, all those fields circulating around add up, and you get this flow of field through the loop. So with this picture, let's go back to the very first demo that I did, which was looking at the displacement of a compass when there was a current-carrying wire sitting over it. OK, so for this wire, current is going to flow, let's see, current is going to flow this way. So on the screen, that's up. So what does the magnetic field look like? Point your right thumb up, your fingers will curl, and beneath the wire, which is where the compass is, it will be pointing right to left. Okay, now the needle will align itself to the external magnetic field. So when I turn this on, the needle should point horizontally here. Let's see. It does. It's perpendicular to the wire. Right? And if I move the wire, the needle should follow it. And not point along the wire, but point along the field, which is perpendicular to the wire. If I loop the wire like this, which way does the magnetic field point in the middle? Current is flowing, was that counterclockwise? So it will point, yeah, up or towards you from the board. So the compass isn't going to respond to that, right? The compass is only measuring the horizontal component. So this doesn't do anything. But if I turn this and move the wire around, the compass should follow the wire. You see it's pointing towards the loop? Can you see that? Yes, you can see that? OK, so what's going to happen if I change the direction of current? Actually, this did not change the direction of current. This will change the direction of current. Nothing. Well, we got it to work once. It's good enough for me. Yeah, I think the fact that the meters are both on 0 and I smell melted plastic is a bad sign. Probably tripped a fuse. OK, and so here's a picture of a wire. Just like here, this was sort of a three-dimensional picture or quasi-three-dimensional picture. Here, it's drawn in the plane of the paper. And the right-hand rule tells us on the top, the field's pointing out. On the bottom, it's pointing in. OK, so that's the magnetic field. It's easy to draw field lines because they always loop around. You just need to know which direction they're going. And for that, we use the right-hand rule in any of these forms. And just like we had electric flux, which was the amount of field that went through a certain area, the flux per unit area, or the field per unit area, we have magnetic flux, the amount of magnetic field that goes through a unit area. So if these blue lines represent the magnetic field, and I have some surface that those field lines are crossing through, then I can talk about the amount of field lines per unit area, the flux. And just like with electric field, the definition is exactly the same. I just replace electric field with magnetic field. So we say the magnetic flux is equal to the magnetic field dotted with the area vector. Right? So if I have a surface, depending on the orientation of the surface, that defines the direction of the area vector. And it's the component of the field that is normal to the surface. That's what this dot product means. That's the part that goes through the surface. Right? The parallel component doesn't cross through the surface. Flux gives us the amount of field that crosses through a surface per unit area. Okay, and magnetic field is measured in Tesla. Area is measured in meters squared. So we get Tesla meters squared for the units of flux. And since there's a lot of things we're going to do that involve flux, that quantity gets its own name. It's called a Weber. So we've got a lot of units to keep track of. Generally, if you keep things in MKS units, the units will work out. Right? So if your head is spinning with all the different units, you can just keep track of what the units should be on any particular quantity and convert everything into MKS units before you start solving problems. That will get you pretty far. So we saw with electric flux that electric flux that goes through a surface, if you have a closed surface, that told you about the amount of charge inside. Because electric fields were only the electric field lines were only created at positive charges. So if you had net flux leaving a surface, that must have meant it was created inside the surface. If it was created inside the surface, there must have been positive charge there. And vice versa. If flux is going into a surface, there must be some negative charge, which it's where the field lines are going to. And that qualitative relationship expressed itself quantitatively in Gauss's law. So the flux equaled, that should be rho over epsilon. The over epsilon is missing there. Okay, so that was Gauss's law. But now we can define a similar thing for magnetism. We have the exact same physical picture. We have field lines going through a surface. That's what flux is. And if I have a closed surface, I can make the exact same argument. That if there's net flow of field, if there's net flux out, there are field lines leaving the surface that must be starting inside the surface. So where do magnetic field lines start? What are the two rules for drawing magnetic field lines? They go from north to south. And what's the second? They're closed loops. So they're closed loops. Do they start anywhere or end anywhere? No, they don't. They don't start anywhere or end anywhere. So can you have a net flux into or out of a closed surface? You can't. Any field line that goes into the surface must come out in order to loop back on itself. So what do you think the analogy to this is? What would change? Two things change. Well, the area is just the area of whatever imaginary surface you want to draw and then integrate over. The electric field changes. Right? In Gauss's law for magnetism, we would replace E with B. Right? What else changes? What does the right side have to equal to? 0. Yeah, exactly. Good. It has to equal the source of magnetic field lines. You could write that as rho of m, the magnetic charge, if you like, the number of magnetic monopoles, but there are no magnetic monopoles. Right? So that has to be 0. So that's Gauss's law for magnetism. So just as Gauss's law for electricity was a significant law that you needed to learn, Gauss's law for magnetism is equally as significant. Okay, so magnetic fields are a little more peculiar than electric fields. Magnetic fields point in one direction, but they produce forces that act in a different direction. Magnetic fields act on charges, but those charges have to be moving. Right? So they're a little more peculiar. We have this expression for the magnetic force. It represents all those things. The charges have to be moving. It's perpendicular to the magnetic field. We can look at that expression, and just from the math, we can derive some really important physical consequences from this. So first of all, what can we say about the direction of the force compared to the direction of the velocity of the charge that it's acting on? Are they? They're perpendicular. Yeah, the force is the cross product of V and B, or in the direction of the cross product of V and B, and so it's perpendicular to V and B. Okay, so if the force acting on the charge is not in the direction of motion, but it's not against the direction of motion, it's not going to speed up the charge. It's not going to slow down the charge. Well, it's a force, so it's going to accelerate it. How can you accelerate something without speeding it up or slowing it down? Yeah, it can change its direction. So the force, I can draw it pretty easily, more easily than I can say it. You've got a charge moving in this direction, and a magnetic force that's acting in this direction, then after some unit of time delta t, the new velocity, v prime, is going to be v plus f delta t, right? Since f equals ma, let's see, f over m delta t. F over m is the acceleration, and acceleration is delta v over delta t. So delta v, the change in velocity, is just f delta t over m. So the force is perpendicular to the velocity, so this vector doesn't get longer or shorter, it just changes direction. So magnetic forces cause free particles that are moving to change direction, but not speed up or slow down. So given that, what can you say about the work done by the magnetic force? Recall, work is force dotted with displacement. Which way is this charge? Which way is its displacement? It's vertically. The force is horizontally. So what can you say about the work done by the magnetic force? 0, yeah. So magnetic forces cannot do work on freely moving particles. Can't speed them up, they can't slow them down. They can only change the direction. And so what you end up with, if you have a moving particle, and let's say you're a moving particle, it's down here at point O. It's moving to the right, and then you suddenly turn on a magnetic field. And that magnetic field is pointing into the page. That particle is no longer going to keep flying left to right. It's now got a force on it. It changes its direction. That force is inwards. I mean, it's going to curve in. As it curves in, it's got a new velocity that's pointing, has a component pointing up. And now, the direction of the force, qv cross b, is a plus charge. V is up. crossed with B into the page, the new force is pointing this way. So as it's curving, the force always points towards the center of a circle. That circle is the circular path that it's moving on. So the charge will move in a circle at constant speed. Yeah, Fred?
Well, is the Q in that equation, is that only absolute value in this case?
Yeah, so let me see. This Q is plus or minus. Right? It could be an electron, it could be negative. The magnitude of the force, I explicitly put the absolute value on just so we get a positive number here for the magnitude. And if you figure out the direction of the force, that's always going to point towards the center of the circle it's moving in. So charged particles move in circular paths in uniform magnetic fields. One of the things you might want to know about the path that this charge is taking is how big it is. What's the radius of curvature? So you could set that the magnitude of the centripetal force, the magnetic force is what's keeping it moving in a circle. So QV times B is that magnitude. The centripetal force has a magnitude of mv squared over r. Right? That's for anything moving in a circle. And now we can solve this for r. Right? So bring r to the other side, divide through by QVB. One of the v's in the numerator cancels with one of the v's that you bring down. And we get the radius of curvature is mv over qb. So if you knew the strength of this magnetic field, and you knew the speed at which a charge is moving, and then you measured the path that the charge took, that would tell you the mass to charge ratio of the particle. Turns out that's really important because different charged particles have different masses, different charge to mass ratios. An electron has the same magnitude of charge as a proton, but vastly different masses. And so an electron and a proton moving in a magnetic field would travel in different circular paths. Let's say this is the path of a proton. It's positively charged. It's moving to the right. What if you had an electron that was moving to the right at point O? What would its path look like? Let's see. Its magnitude of charge is the same, but its mass is much smaller. So the radius would be much smaller. So it's going to be a smaller circle. And would it be the same? Would it curve up? So the direction of the magnetic force is QV cross B. The V is the same. The B is the same. And the Q is opposite. So the force ends up pointing down. An electron would move in a small circle curving down from that point. So this is the way that scientists identify subatomic particles when they collide them at CERN or when they collided them at SLAC at Stanford. They allow those particles to go through a magnetic field, and then they track them, and they look at their trajectory and work out the charge to mass ratio and compare that to the charge to mass ratio of the known or expected particles. Let me just show this slide. This shows exactly that. This is it's called a bubble chamber photo. It's the trajectory of various particles created in a atom smasher. So you have a moving charge, or a moving particle. Oftentimes it'll be a proton or some atoms or ions colliding with some stationary particles. So conservation of momentum tells you after the collision, everything's going to be spraying off to one side. And you can figure out how fast things should be moving. So our trajectories are all moving, let's say, left to right. I don't know if it's left to right or right to left, but we'll say left to right. And this region has a magnetic field, and we see three different types of paths. Some that go straight, some that curl in one direction, some that curl in the other direction. And you can look at those and figure out what types of particles those are. What would go straight? Neutrons. Why do neutrons travel straight through here and not get pushed in either direction? They have no charge. They are not moving charges. So the magnetic force does not act on them. Okay, we will stop there. Have a good weekend.